Vallée. I'm from Nokia Bell Labs France, and I will present some security aspects regarding FPGA offloading in the cloud. So this is the context. We are working on infrastructure for cloud computing with context of Kubernetes, Docker, deployment of microservices on the server. We deploy the microservices on the CPU, and the microservice has access to the FPGA to offload some hard processing algorithm as a DPC, for example, or machine learning algorithms, which need more power than the power provided by CPU. So we had such architecture in our lab, and so we have the CPU, which will receive the microservice, and the microservice will have the opportunity to offload the data for processing to one of the logical array of the FPGA. So microservice will be dedicated to logical array 1 or 2 or n, depending on what the orchestrator decides where to deploy the microservice. This has a little drawback, since if a microservice is deployed on one array and another on the second array, we can have an attacker which would have access to the data dedicated to the other arrays. So we need to secure this. And one first easy solution is to use AES encryption on the CPU side before sending the data to the FPGA, so that the attacker won't be able to decrypt the data coming to the FPGA, even if it's not its own data. The problem of using only AES encryption is that you need to share the AES key to the logical array. So there are two aspects: whether you build the FPGA already with the AES key inside the FPGA, but if the attacker is somehow able to decrypt the AES key, you can change it, or you make it dynamic. That means that you need to send the AES key to the FPGA, but if you do so, you will need to send it through the bus, and the attacker is able to read the AES key. So as soon as he is able to read the AES key, he will be able to decrypt the data. So we use another level of encryption to share the AES key between the CPU and the FPGA. So we will encrypt the AES key with another encryption protocol, which is an asymmetric encryption protocol, in this case, the ECAG. So this is our solution. We will wrap the logical array with a security wrapper with some logic. And inside this logic, we will have a true random number generator in the hardware, which will generate one pair of key, a private key and a public key. The public key will be sent to the CPU so that the CPU can encrypt its own AES key. It will send the encrypted AES key back to the security wrapper. The security wrapper will decrypt the AES key with its own private key. As soon as the AES key is decrypted, the security wrapper will configure the AES engine so that the data coming from the CPU will be decrypted, processed, and back encrypted before sending back to the CPU. And for that, I have a small demo, which is very fast. So I will launch on my server. I will connect to my server in my lab. This is a cloud server, so I can connect from here to France. I will launch my application, and I will specify an AES key, which will be used by the software. And I will request the public key from the FPGA so that I can encrypt my own AES key and send it back to the FPGA, so that when I will send my encrypted data to the FPGA will be able to decrypt the data. I have a small terminal for that. So I already run the demo. I connect to my server. I go to the right folder and I can launch the demo. So here I specify one AES key, which will be used by the CPU. And this AES key is sent to the CPU, encrypted with the received ECAG public key generated by the FPGA. And if I launch again, you will see that this key won't change, but the public key is changed. Before each time we have a request, the FPGA is able to regenerate a new key. So we have now this public key, and before you see it was another public key, but the AES key is still the same. I can also provide another AES key. It's not an issue, you will see. the processing is still a success.